All right, let's dive right into this. Have you ever wondered about the actual algorithmic magic that happens the exact millisecond you finish speaking into your phone and it just instantly types out what you said? Well, welcome to this explainer. Today we're decoding Viterbi Decoding, which is basically the incredible mathematical engine that powers inference and automatic speech recognition. At its absolute core, any speech recognition system faces one fundamental question at test time. Given a sequence of incoming audio, what was actually said? I mean, it sounds simple enough, right? But here's the massive bottleneck. The audio is sliced up into tiny chunks we call frames. If our system tries to just blindly guess the hidden state of every single one of those frames to figure out the sequence of words, the math gets terrifyingly large very, very quickly. So to understand how we actually solve this, here's our game plan for this explainer. First, we'll look at the exponential path problem. Second, how dynamic programming comes to the rescue. Third, the three phases of Viterbi. Fourth, Viterbi and real ASR. And finally, we'll contrast decoding versus training.
Okay, starting off with section 1, the exponential path problem, and exactly why we can't just brute force our way to the right answer.
So imagine our incoming audio stream. Every single frame of that audio could, at least in principle, be mapped to any hidden state in our model. If you sit down and try to calculate every single possible sequence of states from start to finish, the number of possible state paths grows exponentially with the number of frames. The computations just completely explode. Brute force search isn't just a little inefficient, it's mathematically impossible to run in real time. We desperately need a smarter shortcut. And that brings us to section 2, dynamic programming, which is pretty much the ultimate algorithmic shortcut. Enter Viterbi Decoding. By definition, this is an inference process running at test time. Using a fixed, already trained model, it finds the single most likely sequence of hidden states for a given utterance, which then seamlessly map to phones and words. Now, the absolute genius of the Viterbi algorithm is that it finds this best path in linear time rather than exponential time. And it pulls this off by exploiting one incredibly crucial fact. The best path to a specific state at time t depends entirely on the best paths to the states at the previous time step, t-1. Think of this core idea kind of like navigating a giant, complicated maze. As you sweep left to right through the frames of audio, at each room, or state, you only keep the single best, fastest way to reach it. You remember that winning score, and you leave a breadcrumb, a backpointer, to exactly where that best path came from. Because you never ever need to remember these suboptimal, slower ways of reaching a state, the amount of total work you have to do stays linear based on the number of frames. So, how does this actually work under the hood? Let's move on to section 3, the three phases of Viterbi and the actual mechanics of the algorithm. To track our progress through that maze we just talked about, the algorithm uses two main variables in its dynamic programming array. First up is delta. Delta at time t for state j represents the absolute best score of any path ending in that specific state at that specific frame. We calculate it by taking the max score from the previous state, multiplying it by the transition probability, and then multiplying that by the emission probability of our current frame. Second, we have psi. Psi is literally our breadcrumb. It's the backpointer that simply records which previous state actually gave us that maximum delta score.
The algorithm itself unfolds in three really elegant steps. Step 1 is initialize. We just calculate the start probability multiplied by the first emission for frame 1. Easy enough. Step 2 is where the heavy lifting happens, recursion. For every subsequent frame, we calculate and fill in those best scores, the deltas, and we drop our backpointers, the psis. Finally, step 3, backtrack. Once we hit the very last frame of audio, we simply pick the best final state and we follow our psi breadcrumbs all the way back to the start. Now, the absolute key takeaway here, specifically in the recursion phase, is that Viterbi uses a max operator. By taking the max over previous states, it's making a hard choice. It completely and totally commits to the single best path.
Which takes us right into section 4, Viterbi and real ASR. How does all this beautiful, clean math survive the messy reality of practical speech recognition? Well, in real systems, the states aren't just a simple hidden Markov model. Decoding actually runs Viterbi as token passing over massive composed HCLG graphs. That means it's mapping everything from synonyms to context to phones, all the way up to the language model. And because we are multiplying lots and lots of microscopic probabilities together, practical Viterbi works in log space. This turns products into sums, entirely avoiding the problem of numerical underflow, basically stopping our computers from just rounding everything down to 0. Now, the computational cost is roughly big O of t times s squared, where t is frames and s is states. But honestly, with those massive real-world graphs, even linear time can get way too heavy.
So real ASR uses something called beam search alongside Viterbi. This prunes away the low-scoring paths on the fly, keeping the whole process feasible, and eventually spitting out the one best word sequence.
And that brings us to our final topic today, Section 5, Decoding versus Training. These are two very different goals relying on the exact same foundational algorithm.
When you read up on Viterbi, you're constantly going to see it contrasted with another algorithm called Baum-Welch. This is actually a huge favorite for job interviews, by the way. Viterbi training is considered hard EM, or expectation maximization. Because it uses that max operator we emphasized earlier, it assigns every single frame to exactly one state. It commits early. It's cheaper, it's simpler, and that makes it fantastic for generating hard targets to train a neural network. Baum-Welch, on the flip side, is soft EM. It uses a sum operator. So instead of picking one definitive path, it sums over all possible paths. This means a single frame might be fractionally shared across multiple states. Say it's 70% state A and 30% state B. Baum-Welch retains all that mathematical uncertainty, which is definitely more expensive to compute, but it uses more information. So you can really think of Viterbi training as a hard, cheaper approximation of Baum-Welch.
You've also really got to keep the end goals of the algorithm straight in your head. In decoding, which is inference, the model parameters are totally fixed. You run Viterbi because the path itself is the final answer. It's the transcript you want. But in training, which is learning, the alignment is hidden from us. So you run Viterbi to guess the best path just to use it as an intermediate label. You then take those hard labels to update and train your model, repeating that loop over and over until the model is stable. So it's the exact same best path search, but serving an entirely different purpose.
So to sum it all up, the absolute crucial point is captured perfectly by this definitive one-liner from our sources. Viterbi decoding is dynamic programming that finds the single most likely state path through a trained HMM for a given utterance. It initializes, it recurses by keeping only the best path into each state using those handy backpointers, and then it backtracks to reveal exactly what was said.
But as we wrap up this explainer, I want to leave you with a really fascinating question, drawn from the evolution of these systems. That whole hard alignment dance of Viterbi training, guessing in alignment, training, and repeating, is exactly the pain point that modern end-to-end neural models, using something called CTC loss, were designed to completely remove. CTC just sums over all the alignments in one go, requiring no separate alignment stage whatsoever. So as end-to-end models continue to dominate the field, will the beautiful classical dynamic programming of Viterbi eventually be fully replaced? It's a massive shift in how machines learn to listen, and definitely something to chew on. Thank you so much for joining me on this explainer, and as always, keep learning.